And let me begin the slide. Okay, I hope you can all see the slide. Okay, so welcome back. So let me first remind you the homework report is due next coming Sunday. And today we're going to finish the discussion on Ising-anyon and quantum computation. And we're going to discuss the Kitaev chain and Majorana zero mode and relation to this Ising-anyon model. And if we have time, we may go into the next week 8 topic, magic. Actually, this week's topic, magic state isolation and surface code. But before we begin, I'd like to pose the 3 questions. I did not prepare the poll, but I'll just ask. So which model has 4 annual, 1 charge, flux, and fermion, and the fermion is the bound state of charge and flux. Maybe you could type in the chat, or you could just speak out. Yeah, unfortunately, I don't have the poll prepared. So maybe you can type in the chat, let me know. So which model, what model we discussed this that has these 4 annual? I didn't use the poll, so maybe just type in the chat. Yes, it's torical. It's Kitaev torical model. Okay. The second question, which annual model has just 2 annuals, the vacuum identity and 1 other annual, and when you fuse the 2 of the non-trivial annual, it becomes vacuum or the annual itself. Which annual model is this? Yeah, I saw.
Fibonacci.
Yeah. Say that again.
The Fibonacci.
Yeah, this is the Fibonacci, because as you can see, the dimension of that follows the Fibonacci series. Okay. Okay, the third question, which annual model has annual vacuum, fermion, and the sigma? The way they fuse is that the fermion, 2 fermion fuse to vacuum, fermion and sigma fuse to sigma, sigma and sigma fuse to identity and fermion.
The Ising?
The Ising model?
Yeah, this is the Ising-anyon model. Yeah. Okay, that's I think a short summary of what we talked about last time. Okay, but today we're going to focus on this one more, on the last one. Between the second and third annual model, the third one is easier to generate. Okay, okay, so this is the review of the Ising-anyon model. So these are the fusions that we already talked about. The physical picture that I mentioned last time is that the identity is sort of a condensate of pairs of fermion. These pairs of fermion usually called Qubit pairs, which appear in superconductivity. So maybe let me just draw there 2 psi and psi. This is a Qubit pair. okay? And psi itself is a excitation because it costs energy to break the Cooper pair. And sigma is the Majorana zero mode that bound to a vortex. So we remember we have these vortices, and if you draw that, there is a zero mode here. Okay. And so the question that we like to know for encoding quantum information is that, can we find a qubit in the Hilbert space? So if we have two Ising-anyon, it fuse to identity or it fuse to psi. So you may want to naively use the two different channel as 0 and 1 logical space, but they are, the final product are different, so you cannot superpose them. So you need to use something that has a few possibility at the intermediate steps. So that's why we need to look at 3 sigma, and this is how we fuse. For example, we fuse these two and we have 1 plus psi, and we take another one. So 1 and sigma is sigma. Psi and sigma fuse to sigma, therefore we have 2 sigma. So the 2 indicate that there are 2 paths to reach a final state, which is a sigma. Yeah, so then we can use these two possibilities. So 1 and 2 fuse to 1, sorry, 1 into Sigma-anyon fuse to identity, or fuse to a fermion, and then they fuse, finally, both fuse to sigma at the end, okay? So you could use this one in principle, but this is not so desirable because the final product is sigma. It's probably not easy to create isolate sigma in the beginning, so it may not be useful. So we probably would like to have something that the final fusion product is identity. Okay, that motivates us to look into more of the fusion. So you could fuse 4, and there is a space of 2 times the identity. That means there are 2 ways to fuse that. Of course, there's also 2 ways to fuse the fermion. You could also consider 5 of them. There's a Hilbert space of dimension 4 that can be used to encode 2 qubits, but ideally you would probably want to have 1 more. So for this, you would just consider the fusing already is 4 sigma, and then you fuse another one. So that just is 4 times identity plus 4 times fermion. And you might prefer to use this one as the 2-qubit encoding. But you can play with this with more Sigma-anyon, and the upshot is that you need to use 2n sigma to encode n-1 qubit. If you use this identity as the final fusion product. Okay. So that's a review, and we can talk about using these fusion channel and discuss different order of fusing. So remember, we talk about this diagram. This means that this diagram means B and C fuse first to F, and then A and F fuse to D. And this is a different order, then A and B fuse first to E, and E and C fuse to D, and they all end up with final D. This is a basis transformation, and they are related by a unitary. And in this particular case, that you have 3 sigma that fuse to 1 sigma, you've already seen that there are only 2 possibilities. So either identity or psi. It turns out that the 2 bases are related by a matrix. This is just a Hadamard matrix. Okay. So this is the basis transformation. So you're going to see this. This is converting X to Z. But I want to say that this is not an active basis change. This is just a formal relation between the two fusion order. There's one that's active. This is active transformation. When you braid the 2 anion, and this is how it related back to the original. So as we talked about, mentioned this last time, when you fix the fusion of A and B to be, for example, identity, when you exchange the 2, it's a phase. It's a phase, in this case, it's e to the minus I pi over 8. And when the fusion product is psi and you braid the 2, it's a different phase. So, and it's convenient to write in this way because the elements in the matrix is actually a phase Ks. Okay, and this is when you fuse the first 2. But if you want to fuse B and C, if we want to braid B and C, excuse me, we cannot do it directly because in this configuration, B and C has no direct fusion. So what you need to do is you do the basis transformation to take them into the same psi, B and C, and then you do the braiding, that's just a phase, and then you bring this basis back. Okay, so the upshot is that if you do the braiding of B and C, it gives rise to a matrix. So I didn't write down the explicit matrix. Okay, that's the matrix. Yeah. And we have this is if you want, that's this. We can ignore the overall phase. We just copy here. Okay, but what I illustrate here, if you braid that twice, if you braid B and C twice, you get a NOT gate up to a phase. Okay, so next I'm going to look at more gates, braiding operation to generate more gate, but it turns out that Ising-anyon can only implement Clifford gate. So if you do it topologically, but you could also use non-topological method, but in this case, it would not be protected, but you can get non-Clifford gate. But there are also other options that's related to magic state distillation. We'll talk about that later. Okay, but before we go into the detail of the gates, let me just list a few realizations, possible realization. these are related to these Majorana zero mode. So we have, for example, topological insulator and superconductor flux. This probably is the most popular one, semiconductor on top of a superconductor with a transverse field. And there are also other ways to implement that. And to do braiding, if you have a one-dimensional chain, what you can have is such T-like junctions, and you can induce the braiding. We mentioned that, but I will talk about more later. Okay, so we mentioned that we like to encode qubit using the configuration that they all fuse to identity in the end. So if we have 6 anyon, we have possible encoding of 2 qubits. So we talk about this as 1 qubit, but more practically, we might want to use this as a 1 qubit encoding. Okay. But the way that we choose the encoding is as follows. This is one example. You could choose, so you have 6 anyon, sigma anyon, and you want to choose the logical 00 as one that fuse to identity for all 3 pairs. So there are 3 pairs. So if they all fuse to 1, the 3 fuse to 1, and we will choose this as our logical 00. Okay, there are only 4 possibilities, and we fix this one, and we can also choose other possibility. So for example, we could choose the first 2 pair fuse to fermion, and the last pair fuse to identity. So this is okay because you have fermion will fuse to identity, right? So this is fine. The final product of the fusion would be 1, as indicated here. So the other choice for 0-1, logical 0-1, is sort of permuting these two fermion to be the product of the second and third pair. And you could also have the other possibility. The first and last pair has a fermion that encode 1-1. So this is an example encoding of 2 logical qubits. Okay, this is just a choice. But once you fix your basis states, then you have to ask about the gate, right? Okay, and the reason we choose this as 0-0 is because it all fuse to identity, right? So it's maybe easier to create because maybe you could just initialize like 3 segments, and in terms of Majorana mode, I would just write comma comma. Maybe it's easier to create these anyon from vacuum. Okay, locally. Okay, so this box just remind you, if you fix the fusion channel, the way you braid is just a phase. Okay, and this F is a basis transformation, but it has to fix so that you have sigma, 3 sigma, and the final product is also sigma. And it's between 2 different choice of braiding, this versus the other one. Okay. Okay, so there are gates that you can consider. For example, we already have the NOT gate from the previous page, though it's a slightly different encoding, for example, we have 3 sigma that fuse with sigma. If you do the braiding twice on B and C, it gives you a NOT gate. Okay. It turns out that it's similar, that you also have a NOT gate on qubit 1. And you could also have logical Z gate on qubit 1. This is logical qubit X gate on logical qubit 2. This is logical Z gate on qubit 2. You can identify the structure. So this is like braiding twice on 2 and 3. This is just braiding on 1 and 2 twice. This is braiding 4 and 5. This is braiding 5 and 6. So it's really just using the braiding. And you also have the Hadamard transformation. This is the real Hadamard. Real, maybe I need to say active Hadamard. This is what, when you are doing real action, it gives rise to a transformation. Okay. And there's also the control Z gate that you see that just using 3 pairs, 3 braiding. Okay. And I'm going to explain how you get these, how you understand these X1, X2, Z1, Z2 in a moment. Any questions so far? Okay, and also there's nothing in the chat. So let me move on to the next one. But before that, let me just examine this structure here. So this, the first pair fused to A, and then second pair fused to B, third pair fused to C, and they all at the end fuse to 1. Okay, so that's the choice. And it turns out that this is determined. This is determined by A, B, C. Okay. And yeah, perhaps, yeah, this is the table that summarizes the encoding we have. Right, so 0, 0 is A, B, C being 1, 1, 1. 1, 0 being A, B, each has a psi. 0, 1, B, C each has psi. And 1, 1, A and C each has a psi. Yeah. As I said, this is already determined because A, B, C, you can see only even number of fermion, they would always fuse to 1. So this will be 1 here, actually. Okay. No, that's probably not correct because this could be fused to identity, and then this could also have 1. But the other case, for example, this could be a fermion, and this could be a fermion, that's identity, and this would be a fermion. Okay, but what I'm saying is this lag here has no freedom. So once you have ABC, it's fixed. Okay. But I want to actually use a more natural picture of braiding fusion. So for example, you would like to fuse the first 2 and then you fuse the third, fourth, etc. in a sequence like this. And it turns out these 4 is identical to these 4. So maybe let me explain a little bit. So the first case is the first 2 pair fuse to identity. Then the second pair also fuse to identity. and third pair also fuse to identity. But you can see when the first two pair fuse to identity, basically you can ignore that. So you're left with the third particle that fuse with identity. So it continue with what it was before, and then fuse this sigma to become an identity. And the identity fuse with that is essentially just this keep doing what it was and then fuse to that. So that's identity. Okay, so this diagram is the same as this encoding, even though you may see it looks like a different grading sequence than this one. It's different graph, but in this case it represents the same state. And you could also do this for the second one. Let me explain a little bit. So the first two pair fuse to psi, second pair fuse to psi, but we can write the first pair fuse to psi and the second pair also fuse to psi. And you can, in terms of the order, you could look at, for example, psi then fused with the sigma, it has to become a sigma. And then this is the sigma, and sigma with sigma is fused to 1, okay? But because the second pair in the original way of fusion, it fused to psi, the first one has a product psi, so therefore it has to fuse to 1 here. Okay, so these two are in fact equivalent. Okay, and you could also see the third one can be represented this way. This one is identity, okay, and you fuse to psi, but this identity does nothing. So this sigma is the same sigma here, and then it fused to psi. Okay, and then the third pair, if they fuse first, they should fuse to a psi, but because of this psi that fused with the sigma, it's fused to a sigma, and then the last sigma fused with a sigma that should give rise to 1. Okay, so what I'm saying is that these four correspondence is 1-to-1. Even though they look differently, they are 1-to-1. So they are sort of equivalent representation. Okay, it may require maybe looking at again and working through this yourself. You'll realize when you have a sigma, it's sort of flip because it has to at the end fuse to 1. But if you have a sigma, so if you have a psi and psi, it should fuse to identity. But looking at this line here, you have a psi, sigma, identity, sigma. So this here is psi, and this is here 1. So it's different from psi and psi, but this is because the first psi already flipped the sigma into a sigma. Okay, so maybe you should go through that yourself. Okay, but why do I want to mention this? Because using this is easy to understand the gate operation. Okay, so the reason is that, remember, if we want to grade this, the second and third using this picture, we cannot directly braid them. Yeah, but if already have this representation, we could use the grade 2 and 3. We could use this rule here. Let's go back a little bit. we can use this rule, right? We can use this rule to do the braiding. In fact, it says that it's just a sigma X matrix if you braid it twice, okay? So let me just show the simplest one is actually S gate, because R is basically a S gate up to a phase. If you only swap it, if you swap it the first two pair, you already get S gate, okay? Because it does not change, right? It does not change the basis. It's only put diagonal phase, and it put a phase when it fuse. When it fuse to sigma, sorry, when two sigma fuse to psi, there is a non-trivial phase I, okay? And that happened also for this. So therefore, you see that this is the reason why the psi here and the psi here is the one, okay? Okay, and we can, this is just what I said earlier. In order to look at the X gate, we braid this 2 and 3 two times. That give us X. To make sure that it's really the X gate on the first qubit, we need to use this braiding diagram. We really need to use this. So when you exchange the two, then you can use the rule that 2 and 3 braid directly. It would give rise to the action of X gate. Okay, so there are also other, but you see a structure that 1 and 2, if you braid these, there's a Z gate. If you braid this, this is a X gate, right? If you braid it twice. Okay, but the action on the logical 2 is sort of asymmetry in terms of the diagram. It's doing the braiding here. It's the Z2, and if you braid these two, 4 and 5, that's the X2. Okay, you can also see the encoding sort of have a symmetry. So 0, 1. So if you looking at the 0, 0 on the left, 0, 0 has the identity here. Looking from the right, the 0, 0 has identity here, and this one is the 1. So if you look at the first pair and the third pair, then you can easily see the logical representation. And the middle one is needed in order to certify that the fusion was all fused to 1 at the end. Okay, so if you can understand the Z1 gate and X1 gate, then you will be able to understand the Z2, X2. Okay. And then also the Hadamard gate, which is doing the braiding of 1 and 2 first, and 2 and 3, and 1 and 2. But this you can verify by 1 and 2 is S gate, and braiding 2 and 3 is a basis transformation of the S. And then the final S is on 1 and 2, and you can multiply and see that this is Hadamard gate. Okay, and the diagram of the Hadamard gate on qubit 2 is the reverse. It's really a mirror, sort of mirror symmetry in the diagram. Okay, then we could also verify the 2-qubit CZ gate. So, but maybe let me write down the R, which is 1I. Let's ignore the overall phase. And the R inverse is basically 1 minus I. So it says this is doing the braiding 1 and 2, but the reverse. And 5 and 6 also reverse. And 3 and 4 is the R. Okay. So how can we understand this? Let me see if I have a slide that have, okay. That's copy. Let me, okay, we can, let's just R 1 2 inverse, R 3 4, R 5 6. Okay, so if we do 5 and 6, we just look at this, right? Let's see how it evolve. So 5 and 6 do the inverse of the braiding will give a minus I if the fusion product is psi. So there's a minus I on these two. This is identity. Then we do the braiding on 3 and 4, right? 3 and 4. If you have a psi, then you have an I factor, okay? Then 1 and 2, the inversion of the braiding. If you have a psi, you have a minus I. Okay, so this one has minus I. This one has minus I. Okay, maybe I should remove that table. Remove that table. Okay, so, and that's verified whether it is proportional to the control phase gate or not. This is 1, and this is also 1. This is also 1, and minus I square is minus 1. So we get CZ gate, which is 1, 1, 1, minus 1. Okay. I think I have more space, yeah. I want to pause here to see if you have any question. I might not have explained these gates in detail enough. Is there any one particular gate you want me to explain? I can do it again. Any question?
So I guess for the CZ gate, the braiding of 1 2 inverse and 5 6 inverse and 3 4, they don't really have like a timely order as it was kind of indicated in this equation.
Yeah, that's right. So you could, because they commute. So you could, yeah, this is probably yeah, interesting observation that you can do it separately. So if you have a braiding implementation, that actually you can do it separately, and that actually you can see that just one step, right? And for these, you have 2 time step. For the X gate, you have 2 time step, right? If you regard the braiding, and here to do the Hardeman transformation, you need to do 3 time step. Yeah. So it turns out that the CZ gate is easy. You just do the braiding or the inverse of a braiding.
So it's quite the inverse from the superconducting qubit, right?
Yeah, it's yeah.
I see.
Depends on the physical system. Different physical system may have a difficult time implementing certain gate, whether it might be 1 qubit or 2 qubit. In this case, as I said, the Ising-anyon cannot implement non-Clifford gate. Okay.
Thank you.
Yeah, actually, I prepare a few like blank slide here for me to draw on this gate. So maybe let me summarize again. So the S gate we already have, right? X gate we already have by, can I erase this? Okay, by just doing the braiding on 1 and 2, because the only one that's non-trivial is psi here, right? So you can see that the S1 gate, the phase gate, and logical qubit 1 is just braiding 1 and 2, right? It's quite obvious because the psi here is where the non-trivial phase factor will give, okay? And then if you also do the braiding on 5 and 6, the non-trivial one is here. So you can see it induced at I phase factor, right? And this is exactly this, yeah. So you can see that this will give rise to S2, okay? So this, because this structure. And in some sense, the CZ gate take advantage of the encoding here, right? This part here, if you do a braiding on 3 and 4, just ignore 1, 2, and 5, 6. You already have a phase, right? Which give, let me just write here, braiding 3 and 4, you will have a gate which is identity on 0, 0, right? Would also be identity on the 1, 1, but would have a non-trivial I in between. This already can be used to entangle qubits, okay? And the inverse of 1, 2, and 5, 6 is just to make the phase so that it multiplies to a CZ gate. Okay, so it turns out this is the simplest phase gates, and the CZ gate are the simplest gate. I hope you can understand right here now. Okay, if you understand the phase gate, this I phase gate, S, we call it S. If you square that, this is Z gate, right? So this means doing it twice. So if you do the braiding 1 and 2 twice, this is what this diagram indicates. You do it twice, it's a logical Z gate on qubit 1, right? And I did not show that if you do that on the 5 and 6 twice, if you square that, braid twice, you get Z, logical Z gate, okay? So I hope you can understand these diagonal gates. These are easy enough, does not need to invoke this equivalent set of diagram, okay? But I need this in order to explain the non-trivial gate. So let me, for example, if I want to understand why I get a X gate on braiding 2 and 3, let me go to the next slide here. If I want to understand the braiding of 2 and 3, right, if I braid these two, then I can really use the transformation that we have on this. So we can use basically this is a transformation that is really here. So let me go back to the point that I did not. Let me change the color. Okay, this is the part, right? If you do the braiding on 2 and 3, and you will have a transformation like that. So basically it says, let me write this explicitly, braiding 2 and 3, or B and C, will give rise to this matrix. Okay, but I want to relate this matrix to the basis transformation. Sorry, the action of the, this will be, when we say 1, this is sigma, 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 and 1, 1, and 1 psi will be when this is a psi, okay? And we want to see this structure is the same. If you really just see the structure, this is the same here. So if you do the braiding here, this is 1, this is psi. And so the action is really just on these two. It's basically mixing these two, right? And mixing the 3 and 4. So let me just write, so braiding 2 and 3 induce a matrix that mixes 1 and psi, right? So 1 and psi is 0, 0, and 1, 0, right? But it also mixes 0, 1, and 1, 0. Also 0, 1, and 1, 0, but in the same way. So basically, this is a matrix that is doing this, right? So I said this is F inverse RF, F inverse RF, right? So because it's doing 0, 1, so 0, 0, and 1, 0 in the same way as 0, 1, 1. Wait, this is, sorry. Yeah, so this is doing this, yeah. So it mixed the qubit 1, right? It mixed the qubit 1, and it mixed the qubit 1. Okay, yeah, this is where I made a mistake. It's 1, 1 here. The second qubit, doesn't matter what the second qubit is, right? The matrix that makes these spaces only depends on the logical qubit 1. Okay, I hope this is clear. So therefore, the form should be this, and it's really just F inverse RF times identity, or okay, I think it's the other way around. The matrix was not written correctly, but the form is, it should be F inverse RF times identity, right? So doesn't matter what the second qubit is, right? Doesn't matter what the second qubit, you always mix the same. You always mix the same way. Okay, does this make sense? I think I've spoken really in great detail. But if there's a confusion, please let me know. Okay. So this is how we get this gate x1. Yeah, this is what's written here. Okay. And the way to understand x2 is similar. But let me illustrate that also. So let me just say it's really the braiding 4 and 5. Okay, so I use the other blank one. Okay, so now we're going to braid 4 and 5. Okay, we just focus on 4 and 5. And the key point is that because this matrix that we have has 3 sigma fused to a sigma, so we need to find a location, identify part of the diagram, which is really here. So if you don't understand this detail, maybe it's fine. Maybe you can watch the video again, but in order to apply this F matrix, we really need to identify the 3 sigma, like here, here, and here, and fuse to a final product sigma. Okay, so this is where we need to identify. Okay, so when we do the braiding 4 and 5, and it only mix 1 and psi, right? But it really mix 1 and psi, so meaning that 0, 0, this is, they all have 1. 0, 0, and 1, 0 looks the same, so looks the same. And this one, 0, 1, and 1, 1, they are different. That would have a different basis transformation. Okay. So this is how you understand the mixing. So this is the mixing. So therefore you get a identity on the first, and then okay, the xk you need to braid it twice. Okay. So this is why it does not matter the first qubit is, it only the action is on the second qubit. Okay. But the key point is there is a part that should have this structure. That allow you to do the braiding. So maybe I should assign a homework here, so for you to understand. Yeah, this is really a subtle point, but it's worth going through yourself. You just put a no. Okay, but using, if you don't understand this part in that detail, you can just remember what I said. Right? There's a sort of mirror symmetry of the diagram. That if you have a braiding on 2 and 3, the mirror braiding on 4 and 5, like here, will give you the X gate. Yeah. Okay. And then once you understand that, you could also understand the Hadamard gate. The Hadamard gate. So we already understand the 2 and 3 is if you do it twice, it's XK, but you just do it once, and it's really just HS, H, and you just sandwich with the two braiding that give rise to S. So we just really just multiply this matrix. Okay, but the key point is you need to make sure that you are working on the correct basis. Okay. Then the Hadamard 2 would be just the mirror of this braiding diagram. Okay. And these are all the gates that Ising-anyon can implement. So it's a bit limited because as we mentioned, yeah, this is the slide. We mentioned earlier that there's a theorem by Gottesman and Neal. It says that if the state preparation computational basis, you can only apply Hadamard gate, phase gate. This phase gate means S. Hadamard gate, H, and CNOT gate. The CNOT gate is equivalent to a CZ gate, but Hadamard to transform the basis. Okay. Polygate X, Y, Z, and measurement of observable in the poly group. Then if you equip only these capability, such a computation can be efficiently simulated. So somehow this is bad for the Ising-anyon because you cannot achieve universal quantum computation. Okay. So how do you solve that? One naive way is because these anyon, if they are far away, they don't have interaction. If you bring them closer, they will induce some energy. So it just, you need to time it well. And if you know the energy difference, then that will induce some phase shift. But this is not protected by topology. There's no protection. Yeah, so we will talk about magic state dissolution later. Okay. Yeah, so I need to mention also the initialization. We talk about the gates, but we also need to know how we initialize. So it's among these four states, this is the simplest. That you, perhaps it's a vacuum, then you just create a segment and a segment like that, and you could initialize in a 0, 0 state. Okay. Readout, how do you read out? It's also easy to see that the Z readout, the computational basis, 0, 1. If you want to read out the 0, 1 from the first qubit, you see the difference is there's a psi here of the first pair that is indicator of a 1. So what you do is really you bring these anions together and then let them fuse. Okay, so identity is still vacuum, so no change in energy. Okay, if you observe that there's a change in energy because the fermion should have higher energy, then you know I got a logical 1. Okay. So you could also do this on the second qubit, and remember that I mentioned that the second qubit, really the last pair fused to the side that can distinguish. So what you do, you would bring the 5 and 6 anion together, and then let them fuse, and then you can detect energy. As to how you detect energy, that would be physical system dependent. So depending on how you implement these anyon. So, but if you can detect the energy change, if you don't see energy change, no change, that means that's the vacuum. That means it's logical. One. If there's a change in energy, that means it's a psi that you detected. So this is logical, sorry, this is logical 0, and that's logical 1. Okay, so this is how you measure in the Z basis. Okay, you could also measure the X basis. In this case, you could do the detection by fusing 2 and 3. We call that, this is a sort of a basis transformation of F that would sort of transform into the conjugate basis. I'm trying to identify. This is what I mentioned. Okay, so if you fuse 2 and 3, and if you get energy change, then it's a logical plus state of first qubit. Okay. Okay, you could also do it similarly on 4 and 5. Or you could do a Hadamard gate, appropriate Hadamard gate, and then measure the appropriate Z measurement. So we have the Hadamard gate already explained in this slide here, right? So you could do the Hadamard, and then you measure in a Z basis. Okay. Any question? Okay, so at least we cover the initialization gates in the previous slides and readout. So that means we could implement some quantum computation, except that this is not universal. We need to do something else. Okay. Before we talk about something else, let me just mention the possible implementations. We saw in the homework 3 problem. There's a simple Kitaev chain, really the simplified chain that has these anyons that are dangling, or these two are the Majorana 0 mole at the end of a chain. And you can use these two chains to form, these two 0 mole to form a Dirac fermion. So such a fermion will be a non-local. Okay, so you see that in the homework. So there are 0 moles. This is perhaps how you initialize them. If you can control the segments, but I would illustrate more. But this is the simplest Hamiltonian, has no other parameter you can change. In this particular case, this is really a non-trivial topological phase. Okay. And remember, we mentioned the Jordan-Wigner. You can transform the fermion back to spins. You find that this is actually the Ising, the simplest Ising interaction, Ising chain. And Ising are either all pointing up, okay, but this is in the Y direction. I mean, just put a label Y, or down. So this way we understand the degeneracy at the end, okay? These 2 0 mole allow you to have a Dirac fermion. You can occupy or not occupy that Dirac fermion. It's equivalent to this spin or pointing down or pointing up in the fermionic chain. Okay. So this is a non-trivial, but so I mentioned a non-trivial phase, but I want to give you an example of a trivial phase, which really just fermion on each side has an energy mu. Okay, And really, if you, in terms of the gamma particle, they are really on site. So the gamma are on site. In contrast to these, this case above, the sort of the pairing or the entanglement is between the gamma on different sides, and they are linked together. For example, you can see in this Hamiltonian. But when you see this trivial phase, this will be gamma at x and gamma b at x, gamma a at x. Okay, it will be proportional to this. Okay, so this is a trivial phase. Okay, and you can write this Hamiltonian in more general way. Allow, for example, different parameter t, delta, and mu. So we already saw mu there. It's a chemical potential. It can be controlled by a gate voltage. T is the hopping, meaning that an electron can hop from x to x plus 1 or vice versa. Okay. So, for example, this representing you annihilate a fermion at site x, and then you create a fermion at site x plus 1. So that means it's a hopping. Okay. And they all have strength T. And here is the so-called pairing, Cooper pairing. But this is so P wave. Okay, this subtlety, if you don't get this, is fine. The pairing is in the sense that you pair two fermion. So you either remove two fermion or create two fermion, and that pairing strength is delta. Okay, but these are parameters that could probably be tuned experimentally, especially the mu parameter here. And as we saw earlier in the represented models, there are two phases. So the constraint is that if the chemical potential is small enough, right? Chemical potential representing the trivial on-site strength. If it's smaller than the hopping, much smaller, then you are in the topological phase. That's represented by, so the pairing among sort of the, this, maybe I call this entanglement between neighboring sites. So they are entanglement using these, indicated by this shaded box, okay? But the other regime is trivial, and so represented by, this is on-site gamma, okay? So what this means is a gate voltage can be used to tune which phases, right? But you could imagine also you could, let me go, maybe go to the next slide first. Okay, you could imagine different region, you have different gate voltages, and they have, for example, in this region, it's topological, so you have 2n 0 mode, but in here you don't. And here you also have 2, right? And you can locally tune the gate voltage, so you have segments of change. So for example, this could be a realization of 1 qubit. The first two fuse to 1, the second pair fuse to 1 as a logical 0, or when they both fuse to fermion as logical 1. Okay, so let me go back a little bit. Yeah, so I mentioned this, you could use a non-local encoding of a fermion. So this fermion will have a mode here and a mode there, and you can ask whether the fermion has occupied the mode or not. That this fermion is, do you have a fermion or not? So the fermion number is, is this operator D dagger D, okay? And then the parity, so parity. If you have 0n, we just call this n, if n is 0, then the parity will be 0. Sorry, will be, let's use plus parity, plus 1. If n equal to 1, we have negative parity. Okay, so we can define operator Pf is 1 minus 2 times the number. Okay, so, and if you do the calculation, this is proportional to the gamma 1 times gamma 2L, basically the product of the two gammas. And in this case, that they both fuse to vacuum, parity is plus 1. So therefore, this I times gamma 1 times gamma 2L acting on this should give a minus sign. Okay. And this will be the plus sign. So this is the negative of the minus PF. This minus PF. But I want to mention that this is not useful for encoding because you have one fermion or no fermion. But when you detect it's either 0 or 1, you have no way to make superposition. So that's why it motivates us to use encoding like this that I already explained. Okay. Yeah. So in the last few minutes, I mentioned that how do we braid these? We call it Majorana fermions. So this is probably not a good terminology. So maybe we should use it's 0 mole. How do we braid these 0 moles? If you have a T-junction like this, so imagine these segments. These can be created. The segments can be created by changing the local gate, by tuning local gate. Okay, it could be in behind this a substrate. You have a substrate that can apply local gate. And the way to do the braiding is that suppose you have two segments here, then you change. There's a extra segment going out. If you change the local gate so that now this segment becomes topological, so that means you bring this anyon to this end, and then you could move this, gradually move this to the segment here, and then you move this to the left, and then gradually drag it to the left part, and then return that anyon to the other side. So you can do the braiding. Okay, so, and that's how it looks like. Okay. So this is how one may be able to do the braiding, even though the geometry is one-dimensional chain, but you use an additional T-junction to do that. Okay, so maybe let me mention some of the challenges using these Majorana 0 mole for quantum computation. So we do the braiding to implement gates, and it's topologically protected. However, if you have anyon that you don't want, right? If you have a region of anyon and you do some braiding accidentally through some unwanted anyon, then that would induce an additional unwanted gate. Okay, so, and this could be done, these anyon that you don't want may appear when you are tuning these gates. So when you maybe change the gates not slowly, or maybe there's some fluctuation, your gate voltages that induce these unwanted anyon. In this particular case, there is a proposal that you use, instead of the gate, you use sort of energy, charging energy in terms of Coulomb interaction to do the braiding. Okay, but I don't want to talk about detail, but because there might be other problems, but this is one particular example that people solve the issue. A second problem could be that in this setup of semiconductors on top of a superconductor, there are Cooper pair that could tunnel into the wire, and this is the external reservoir. So this is external reservoir. Ideally, if there's no such external reservoir, then these qubits are isolated and they are protected from any error, for the error that because of the fermion parity is conserved. Okay, but because we use this superconductor to engineer these zero modes, so it's not possible to remove these as wave superconductor. And this might lead to unwanted tunneling of excitation. These maybe additional fermion would tunnel into that, so that would change your system in a way that you don't expect. However, there are some experimental progress that actually suppress such things, such events. They use some heterostructures for topological nanowire, and they can demonstrate these long coherent time about 1 minute. Okay. And there's also an issue of if you are sitting at finite temperatures, how do you protect against these anyons that may exist because of finite temperature? There's still some probability, right? There's Boltzmann factors. So then you want to engineer a system with large energy gap. So this is where using the Kitaev chain setup is better than using the intrinsic P waves, the vortices, because the energy gap can be engineered and it can protect the localized states on these N modes. But what I want to say is that even though the Majorana fermion are closer to the topological quantum computing, but there's still no evidence of the braiding. There's some strong evidence of the existence of these modes, but there's no observation of braiding. So I think once you observe the braiding, verify that it really behaved as we expected for Ising-anyon, then this will be a really big step toward topological quantum computation. Okay, so maybe I would end here because the next slide will be week 8 topic. So I want to pause here to see if you have any question. Okay, if not, we'll end today's lecture here and see you next time.